Hi everyone, I'm Jilan from Fudan University. I would like to share our work, learning open vocabulary semantic segmentation models from natural language supervision. This is a joint work with Wei Di from Shanghai Jiaotong University and Shanghai AI Laboratory. First of all, let's have a brief recap of the traditional semantic segmentation task, where the training and testing sets share the same set of object categories. That means the model is limited to the closed set of predefined categories and cannot segment novel categories, which is not very practical in real-world scenarios. In this paper, we focus on open vocabulary semantic segmentation, where the model is first trained on the image caption data and then transferred to any segmentation dataset in a zero-shot manner. There have been some recent works that leverage the pre-trained clip model for open vocabulary semantic segmentation. They kept the text encoder frozen and trained the network with pixel-level masks. Another work, Group VIT, adopted image caption data to train a grouping vision transformer for open vocabulary segmentation model with zero-shot transferability. However, the model requires extensive image caption for pre-training. Here, we show that our model not only supports mask-free training and zero-shot transfer, but also it can be trained in a data-efficient manner. Training on web-collected image caption data is quite challenging as the captions only provide coarse image-level descriptions, and the diversity of data is very large. Here, we exploit a key factor in image caption data, termed as visual invariance. To be specific, there are multiple images in the dataset that contain a shared entity, for example, cat, and they have different natural language descriptions. We align the cats in different images with the same word concept to achieve the visual invariance. In this slide, I give a brief overview of our model architecture. The model takes two steps to process the image and the caption. The first step is visual grouping. The visual encoder takes the image and a set of learnable group tokens as input. The image encoder incorporates a slot attention-based binding module and a naive vision transformer. The image tokens are dynamically clustered into different groups in a binding module. The second step is group text alignment, where the average group tokens are aligned to the sentence embedding of the raw caption via contrastive learning. Then, we introduce two proxy tasks to learn the visual invariance. The first task is termed as mask entity completion, as shown in the dash box in the figure. The text encoder takes a mask sentence where all the entities in the sentence are replaced with a special mask token. We append the lightweight transformer decoder that takes the mask caption as input and cross-attends the visual groups. In this way, the mask entities can be completed by querying the visual groups. The completed embedding is aligned to a prompted entity embedding, which can be viewed as the answer to the mask caption. The second task is cross-image mask consistency. In this task, we enforce consistent mask predictions between images that contain shared entities. As shown in this figure, we forward both images to the image encoder and choose the subgroups that match the concept of cat. Then, we obtain two sets of masks of cats by multiplying the image tokens with one image subgroups from different images. Finally, a pairwise dice loss is computed over two sets of masks. The authors can refer to the paper for more details. And the overall loss function is the sum of image caption matching loss, mask entity completion loss, and cross-image mask consistency loss. To enable data-efficient pre-training, we filter the noisy CC 12 million image caption dataset by only keeping those that contain 100 commonly appeared entities. For example, shirts, cats, dogs, and buses. Note that we discard non-visual entities such as view or illustration as usually do not correspond to any visual objects in the image. After training, the model can be transferred to any segmentation dataset in a zero-shot manner. Notably, we do not use any manual masks during training. Here we can see from the red lines in the table that our model with zero-shot transfer even outperforms the model with full fine-tuning on Pascal VOC. Compared with the concurrent work, ClipPy, which pretrains their model on 134 million in-house dataset, our model achieves comparable results by using only 3% data for pretraining. Also, our model outperforms most zero-shot semantic segmentation models even without training with mask annotations on the scene classes. As shown in these figures, the mask entity completion loss improves both visual grouping and group text matching. It also surpasses a series of variants such as single entity masking or mask language modeling. Compared with the baseline method, where the only image caption matching loss is adopted, our model achieves better segmentation results with the help of mask entity completion and cross-image mask consistency losses. There are also some potential future directions that can improve the model's performance. For example, how to better handle the background classes as they are usually not mentioned in the caption. Besides, the segmentation anything model can also be applied in a framework to improve the visual grouping. And our code and data are publicly available. Thank you for your time.